Hello and welcome to Physical Attraction. In the last episode of our ongoing nuclear fusion saga, we talked about how Z-pinch machines and stellarators were both tried by scientists in the West in the 1950s and 1960s, but both suffered from various kinds of plasma instability. The stellarators could confine plasma reasonably well, but struggled to heat it to the necessary temperatures and densities before particles diffused away to the sides. Pinch machines could heat plasma to much higher temperatures, but instabilities prevented them from confining plasma for any reasonable length of time. In the UK, the Zeta experiment had caused a great deal of hype surrounding nuclear fusion, but its neutrons turned out to be from collisions and not thermonuclear fusion reactions, and even when these were achieved that same year, instabilities plagued the project. Bigger machines, bigger budgets, and disappointment led to the doldrums of the 1960s. Meanwhile, in Russia, a design that combined aspects of the stellarator and the pinch machine, the Tokamak, was being developed. The initial spark arose when a bright sergeant called Oleg Lavrentiev wrote to Stalin with his idea for a fusion power source. Eventually, Sakharov and others came up with the initial idea for the Tokamak. His early calculations suggested that you might be able to achieve nearly a gigawatt of power. That's more than 2 normal-sized power stations, and on a par with the largest solar array that's currently been constructed. Now, this machine that would achieve this gigawatt of power would have a radius of around 12 metres, with a magnetic field of around 5 Tesla. And neither of these parameters were really that unreasonable at the time. More ambitious were the temperatures required. A cool, not especially, billion degrees Celsius. Some of the earliest people to work on the theoretical physics of plasma and the magnetic fields involved were the very same people that we've discussed in earlier episodes, people like Kurkatov and Sakharov, who were being detained in Atomgrad-type technical prisons, more or less forced to work on the bomb. In fact, it was the sadistic head of the NKVD, Beria, who first signed off on any funding going towards controlled thermonuclear fusion experiments. Amazingly, the exact same phenomena happened in the USSR as it did in the West, when the amateur scientists Ronald Richter and Juan Perón claimed to have cracked fusion. Kurkatov quickly took advantage of the press furore and the situation to propose a similar project in the USSR. Lev Artesimovich is one of the scientists really credited with helping to make that tokamak into reality. Over the next decade or so, experiments took place in small tokamaks, the largest only around a metre in size, but with successfully higher magnetic fields. I'll stick to units of Tesla for measuring magnetic field strength, even though, as you probably know, 1 Tesla is a pretty big unit. A fridge magnet is around 5,000th of a Tesla, an MRI scanner will go between 1 to 3 Tesla, the LHC is at 8 Tesla, and the record for any stable magnetic field generated on Earth is 45 Tesla. This is nothing compared to some crazy astrophysical objects like magnetars, which are incredibly fast-spinning neutron stars that have huge magnetic fields due to the intrinsic magnetic moment of the neutrons. These can get up to billions of Tesla, but we can't exactly bring one down for use in earthly tokamaks. If, of course, we could bring down various astronomical objects like this to Earth, we just get the best fusion reactor there is, which is a star. So these early Russian tokamak experiments were operating with machines about 1 metre across that would fit on a large desk, with magnetic field strength around that in an MRI scanner. But even these small devices were enough to reveal and correct some early instabilities, and by 1962 they'd already discovered the disruption instability we mentioned. A tokamak's plasma is kept stable by the current that runs through it and pinches it into place. But if that current is interrupted even for a microsecond by fluctuations in the motion of the plasma, you get these disruptions that violently throw plasma into the walls of the machine, sometimes causing a great deal of damage. Amongst the other issues they discovered were those of impurities in the plasma. Try as you might to ensure that your plasma is entirely hydrogen-deuterium fuel, inevitably ions of other species will get in there, including beryllium, carbon, oxygen, neon, and argon. The issue is that some of these elements won't be stripped of all of their electrons. For example, to strip argon of every electron requires more than 3 kilo-electron-volts of energy, or 34 million degrees Celsius. Any less than that, and instead the remaining electrons in argon will get excited into higher energy levels due to collisions with other particles in the plasma. They can then rapidly de-excite, emitting photons of radiation, and, as they excite and de-excite and emit these photons of radiation which go away in all directions, some of them aren't reabsorbed and energy will escape the plasma. So the little impurities acted as highly efficient cooling devices for the hot plasma, which is frustrating if you're trying to get it up to fusion temperatures. 80 to 90% of the energy supplied to early tokamaks could be radiated away by these impurities and by other processes. At the same time, electrons can be captured by these nuclei in a process called recombination, which also results in radiation of photons and loss of useful energy from the plasma. And finally, of course, we've already talked about the Bremsstrahlung, that is to say, charged particles are accelerating due to the magnetic field as they go around the tokamak, and when they're accelerated they emit radiation. Now, you can live with all of these things as a fusion reactor, providing that you're producing enough energy through fusion to replace that loss due to breaking radiation, but the impurity ions have virtually no chance of fusing in these temperatures, so all they really do is drag the temperature down. Another important discovery during the early days of tokamaks was something called the safety factor. To explain this, we'll need to get into the physics of charged particles in magnetic fields a little more. So we've talked about how the magnetic force pushes particles in a direction perpendicular to their velocity, as if towards the centre of a big circle. It's this perpendicular acceleration that causes charged particles to rotate in orbits around the magnetic field. Now that's true if you imagine particles in a single 2D plane, as if rotating on a piece of paper with the force directed to the centre and the magnetic field passing right through it. But perpendicular to that plane, along the lines of the B field, there's no force. So if the particle has any velocity in that direction, it continues to drift. This means that the natural orbit for a charged particle in a magnetic field is a helix, like DNA, orbiting around a point that slowly drifts, spiralling and moving forwards, twirling towards freedom. So the particles in a plasma, until they collide, are orbiting around the centre of the tokamak, moving in a circle, but they're also drifting around that circle following a helix. If you imagine a helix that bends into a circle, you'll have an idea of the basic trajectory of these particles. What the Soviets discovered was that if the particles drifted around the circle more quickly than they orbited the centre of the tokamak, you saw fewer instabilities. Specifically, the kink instability, the one where bulges of plasma became exaggerated over time and gradually hit the walls, that was defeated, provided you could set things up so that the particles drifted around the circle more quickly than they orbited in the tokamak's big donut-shaped chamber. But to force them to rotate around this axis faster than they drifted around the tokamak's chamber, you basically needed to have more powerful external magnets or a reduced pinch current in the tokamak. The pinch current determined how fast they went, and the external magnets determined how close and how rapid those orbits would be, based on something called the cyclotron frequency, which we won't get into too much now, but it depends on the charge, the magnetic field, and the mass, basically. So reducing the pinch current and having more powerful external magnets were things that you could do to improve the stability of the plasma, at least for this one type of instability. So many of the little additions made to improve the tokamak followed a similar pattern to the development of fusion reactors in the West. Remember the guys who took some conducting metal and put it inside the inside of the torus, hoping that it would suppress instabilities by allowing a charge to build up and repel chunks of plasma as they drifted away from the main bunch? Well, this whole idea of using the lens force law and the opposition and the image charges and so on to improve the tokamak was also done in Russia by the tokamak scientists. By the mid-1960s, the Russians were getting impressive results. It may only have been for milliseconds, but the tokamak was capable of confining plasma for 10 times longer than any other machine, and at far higher temperatures than the stellator could achieve. Now, when the Russians first announced these results, it caused a great deal of debate in the fusion community. The reason was all to do with this theoretical formula that those in the West had developed. So you'll remember that the main problem with the stellator was plasma diffusion. Diffusion is this pretty universal phenomenon in physics. If you ever sprayed a can of aerosol in a room, you've seen diffusion in action. The metaphor they used with us at university was that of drunk students staggering away from the pub at closing time. Under classical diffusion, particles collide with each other as they move. Every time that happens, the direction they travel is randomised, a so-called random walk. The result of a random walk is that gradually, over time, you move away from where you started. In fact, assuming that you move at a constant speed, and over a very great number of steps, the distance you end up from where you started is proportional to the square root of the time that's passed, the square root of the number of steps that you take. This is the same formula that gradually allows dye to spread through water, or aerosol droplets to spread through air, quickly at first and then more gradually. I think this makes intuitive sense if you consider stumbling around randomly. Initially you might stagger quite quickly away from the point that you started from. After all, your first step will always take you a full step away, and the second one is quite likely to cause you to move further. This corresponds to the steep slope at the square of the square root function. but gradually over time you're less and less likely to move directly away from your starting point, because if you think about it, there are more directions that you could turn in. The square root of 25 is 5, the square root of 100 is 10, and the square root of 400 is 20. Obviously the square root grows slower and slower as time goes on, although it does always increase. So diffusion and random walk are, of course, far less efficient than running directly away, although if you do stop to solve the diffusion equation, you probably will be eaten by that dinosaur. Early plasma physicists had hoped that diffusion would be totally classical for the plasma. This would mean that, due to the way collisions depended on the field strength, which determines how quickly plasma rotates around the centre of the tokamak amongst other things, the diffusion rate would be proportional to 1 over b squared, that is, the square of the magnetic field. Instead, from analysis of many of the plasmas that had been generated in experiments, plasma physicists thought that turbulence in the plasma, its interaction with the electrical and magnetic fields, were causing diffusion to occur much more quickly and scale as 1 over b. In other words, for a given magnetic field, the theory, called bone diffusion, predicted that plasma would diffuse out of the tokamak far more quickly than could be expected. This would mean that confinement would require impossibly high magnetic fields or impossibly large reactors, and certainly achieving what the Russians had claimed to with the tokamak would be impossible. Spitzer in particular had concluded that the bone diffusion must be true for all plasmas, and this in part led to this great pessimism of the doldrums in the 1960s. Maybe fusion wasn't possible with magnetic confinement at all. Maybe no matter how much you increase the magnetic field or the temperature, the particles would just diffuse out more quickly than they could generate net energy. It's difficult to overstate what a big problem this was for the fusion physicists in this time. The optimist among them had hoped that they might have a working reactor by now. Instead, budgets were spiralling, there had been several premature and embarrassing announcements of fusion success, and now the best theory of plasma physics available suggested that it might be impossible to make magnetic confinement fusion work at all. At the weekly meeting to plan the Stellarator Model C, physicists threw darts at a photograph of Bohm. People were calculating these wonderful machines and then they turned them on and they didn't work worth a damn, said Harold Firth, one fusion scientist working at the time. Plasmas were capable of all kinds of nasty, turbulent behaviour. There were divisions in the community too. Some argued that experiments should focus on an understanding of the fundamental physics of plasma, so that machines could be built that might suppress instabilities. Others, especially experimentalists, noted that you didn't need to understand everything about how a machine operated to use it. After all, flushing toilets had been used for centuries already, even though theoretical physicists couldn't yet totally explain the turbulence of the water in the vortex. On the other hand, this approach had its own disadvantages. In 1966, a government review went down to the Culham Fusion Laboratory, which is still one of the largest fusion laboratories operating today in Oxfordshire, and noted that, quote, 99% of the people were not even thinking about fusion power, just plasma physics. Now, the government reviewers certainly didn't see the necessity, or even the value, in learning more about plasmas in this way, and Culham's budget was slashed in half. It would be a little bit like if the Large Hadron Collider said, we're not actually investigating fundamental particle physics, but we're going to make you a new energy source, and then the government came in and thought, hang on a minute, you're not doing anything about making a new energy source at all, you're looking for this Higgs boson thing. So, when arguing for a basic science program to achieve fusion development, the scientists used a specific and wonderful analogy for the perils of committing to one type of technology too early. Here it goes. A primitive culture decides that it's going to go to the moon. They've just invented the balloon, which allows you to go up, so they have the bright idea of building better and better balloons. Each balloon goes higher than the last, and so naturally the balloon scientists conclude that in a few decades they will have built a balloon that can take them all the way to the moon. The point they were trying to make is that you need to understand things about gravity, space, atmospheric pressure and dynamics, and astronomy before you can go to the moon. You can't just assume because you're making incremental progress that the route you're on is really the best one. But to those funding the project, and those who thought that bone diffusion was a real killer for any working fusion reactor, it may have seemed like the entire field of magnetic confinement fusion was just an exercise in spending more and more money, and more time, on moon balloons. The pessimism was real, especially when Lyman Spitzer retired in the mid-1960s. Now at the time he protested that he'd merely contributed all he could and had been replaced by a younger, better generation, but many assumed, well, here's the founder of the field and he's given up on fusion entirely. A theorist called Fryman said at the time, "As far as we were concerned, it was the end of the world." This Bohm diffusion formula was an empirical law. It came principally from observations, but it didn't yet have a full theoretical explanation until the 1970s. So for this reason, it wasn't impossible that there might be some way to get around this apparent diffusion limit. It wasn't derived from some universally accepted law of physics. But it did seem to hold pretty well for all the machines that the Western scientists were using, which made them very sceptical of the claims about the tokamak. Sometimes laws start off as empirical, just observations like, things tend to fall down, and you later discover the more fundamental theory that means they're always true. Sometimes, though, there are ways to get around them. When the Soviets initially announced their tokamak results in 1965, Bohm diffusion seemed to be this ironclad limit, although results at the Model C stellarator and using a new kind of multipolar field for plasma confinement seemed to suggest that maybe it wasn't totally universal. Nevertheless, the US scientists in particular underestimated the Russians and were sceptical of the idea that they'd produce machines that were an order of magnitude better than the US had managed at this stage. Things came to a head at a pair of international plasma physics conferences in 1968. The Russians claimed to have heated their plasma to 1 kV or 10 million degrees Celsius, and to have confined it for 50 times the supposed limit due to Bohm diffusion. So that's not experimental error, that's clearly violating this so-called law of Bohm diffusion. There's a bit of a mirror image here. I mean, the Russians were working on pinch machines at the same time as the US scientists, and they came over in the 1950s to warn that sometimes you'd see neutrons that weren't the result of thermonuclear fusion. This was before even the embarrassing Zeta episode, where the scientists had to admit that the neutrons didn't mean they'd achieve fusion at all. Now, Spitzer was telling the Russians that they couldn't possibly be right, and warning them that their means of measuring the plasma temperatures were inaccurate. We've talked about this before. How do you measure the temperature of a plasma? You can't stick a thermometer in it that goes up to 10 million degrees Celsius and then read it in a millisecond. It's just impossible for any sort of traditional mechanism to allow you to measure the temperature of something so hot that exists for such a short amount of time. The Soviets, then, were still diagnosing the temperature of the plasma from the properties of the magnetic field. In any plasma, in any gas that's in equilibrium, the temperatures follow what's called a Maxwellian distribution. It's a lot like a bell curve with a very long tail at the end. There will be a small number of particles, by hook or by crook, that are substantially faster than all the others, and there will be a small tail too that has zero velocity. Spitzer reckoned that the Russians were just measuring the temperature of these anomalously hot electrons and not the centre of the distribution. This was more or less exactly the error that Zeta scientists had made when they'd assumed that they had reached fusion temperatures and hence that their neutrons must be from fusion. The Russians insisted, though, that they'd achieved this temperature across the whole plasma. Meanwhile, the British had been working on ways to avoid future embarrassments like Zeta. So they hadn't got a good enough idea of what was going on in the plasma in Zeta, and that's why they'd been deluded into thinking that they might have attained fusion. They were relying on measuring neutrons as a sign that fusion had been achieved, but they could be produced in other ways. So to understand the plasmas and to use their experimental results, they realised that they needed more accurate measurements. In the late 1950s, the laser was invented. I won't get into the details of how it operates too much here because we'll have to do episodes on this, but suffice it to say that lasers produce intense monochromatic light. And when I say monochromatic, I mean monochromatic. There are a range of wavelengths that will look almost exactly the same shade of red to you or I, but the laser produces light at almost exactly a single wavelength. This is because all of the photons come from the same atomic transition, and so they're produced with almost exactly the same energy. And the energy of light determines its wavelength and, in the visible spectrum, its colour. This is important because it means that you can use slight changes in the wavelength of laser light as a means of measuring temperature. So basically what happens here is when you shine a laser through the hot plasma, some of the electrons actually collide with the photons of the laser and pass on energy. It's called inverse Compton scattering if you want to look it up, but basically just imagine the electrons smashing into the photons and making them go a bit faster or a bit slower. If the photons and particles were left to collide with each other long enough in some imaginary box, eventually they'd all reach the same temperature. As it is, the photons end up with slightly more energy than they had originally after passing through the plasma. By using a laser that's less hot than the plasma, you can measure the increase in energy from the laser photons after these collisions and determine the temperature of plasma that way. Bear in mind that we're talking about 1969 here, the height of the Cold War. The proxy war between the US and Soviets in Vietnam was still going on. The Soviets had rolled tanks into Czechoslovakia the year before. Nevertheless, Artisimovich, presumably at some personal and political risk, requested that they send 5 British scientists, later known as the Culham Five, to the Soviet Union with their lasers, to settle the dispute once and for all. There's actually a memoir by one of the Culham Five. Dr. Forrest wrote a book called Lasers Across the Cherry Orchards about his experiences. When they came up with a new way of measuring the temperature of plasmas, they could hardly have expected to be invited across the Iron Curtain. The decision was so sensitive that the UK Cabinet had to clear the trip by vote. After all, these people they were sending knew Britain's nuclear secrets. If one of them turned out to be a secret traitor or something, this would be a very embarrassing situation. Potentially a very dangerous situation. At the same time, they were about to work very closely with the top nuclear scientists from the USSR, at the height of an era defined by nuclear secrecy. Nevertheless, for the good of the science they went. After all, the Russians needed the British to help them measure their plasma temperatures and give them valuable experience with lasers. And the Western fusion scientists were at the end of their tether with stellarators and pinch devices. If the Tokamak did work as well as the Soviets claimed, then it was clearly the most promising path to fusion yet discovered. On such quid pro quo pragmatism can great deals be struck between rivals. Dr. Forrest says that while he was there, he knew they were being monitored continuously by the KGB, who let them know of their presence in subtle ways. For example, the British scientists, thinking they were alone, might discuss that a light bulb was about to burn out, and then the next day they'd find that it had been changed by someone or other. I'm reminded in modern Russia of US Ambassador Michael McFall's anecdote of being left a copy of the Russian version of the Kama Sutra after his wife came to visit. While getting used to day-to-day Russian life and to startled looks they were getting when they walked through the Moscow streets, the British team set about adapting the equipment they had designed to the novel Tokamak machine. This meant opening up the torus to fit windows and a collimator, setting up vibration-proof optical benches for the laser, and aligning its beam through complex optical systems. The activity was frenetic, and the technical problems meant the Russians grew impatient. Nerves, said Forrest, were getting frayed. This did not prevent the Russian hosts, both high officials and the man on the street, to be very kind to their foreign guests. He recalled, "We got the VIP treatment from the authorities. Bolshoi Ballet, Swan Lake and Sleeping Beauty, of course, but also the rare privilege to visit the treasury in the Kremlin and see the Russian crown jewels. Colleagues invited us for ski outings, and when we were by ourselves, in the Moscow crowds, people would stop and warn us about early signs of frostbite. In trams and buses, they would go out of their way to get correct change for us." Aside from some playful monitoring from the KGB, though, the expedition was a scientifically productive one. They shone a laser beam at the Tokamak's plasma, and soon realised that the Russians were indeed telling the truth. The plasma had reached a temperature of more than 10 million degrees Celsius, and the Tokamak design really was confining plasma for a much longer length of time. This moment was pivotal in the history of nuclear fusion. There had been pretty strong pressure in the scientific community in the West to start building Tokamaks, which seemed to produce these undeniably superior results. But almost immediately when the Culham Five came back with news that their hype was real, the older designs were sidelined. The race from the early 1950s was back on, but this time it was all about Tokamaks. Before long there were dozens of designs. The Texas Tokamak, the Doublet Tokamak, Altacore, Ormac, the Symmetrical Tokamak. The last of these was Lyman Spitzer's beloved Model C Stellarator, which was hastily transformed into a Tokamak. Now, there was a great deal of debate at the time about whether this really was the right way to go about things. After all, it was coming up to 20 years since the first optimists had suggested we might have fusion working in 20 years' time. Funding was available, but not no questions asked like in the early days, and the expectations about how much it would cost had skyrocketed. Given that, did it really make sense to build half a dozen slightly different Tokamaks exploring all of the possible routes to fusion through Tokamaks, rather than exploring many different devices? Just because Tokamak devices were performing the best at the moment, they didn't necessarily imply that they wouldn't ultimately lose out to Stellarators, or some modified pinch device, or even some design that no one had thought of yet. But on the other hand, it was becoming clear that a monumental effort would be required for magnetic confinement fusion to work. If funding, science expertise and time was divided between projects, maybe none of them would ever succeed. This debate is still going on today. People are still operating stellators and they're still operating pinch devices, and yes, it's contentious. To an extent, the political nature of scientific funding, especially in the United States, came into play here. It's far more persuasive to tell someone outside the fusion field that our latest device broke all records for confinement time, rather than saying, our latest device, although not as good as what the Russians use, allowed us to greatly improve our knowledge of plasma physics. Which group do you think gets the money from a funding board? So the fusion community faced this dilemma. Diversify and risk being too slow and losing your funding, or throw your eggs in the Tokamak basket and hope that the most promising looking route did indeed pay off. And by and large, in the 1970s, they chose the latter. And not only in the US. Before 1969, there was only one Tokamak outside the Soviet Union. Since then, Tokamaks have been built in over 29 countries, including the USA, Japan, Britain, China, India, Korea, Iran, France. There have been over 200 Tokamaks constructed in total. And in fact, although our understanding of plasma physics and fusion physics has advanced and the design has become improved and more complicated, it is essentially the Tokamak concept that we still use today. The vast ITER fusion experiment under construction in the south of France is a Tokamak. This is not to say that people don't still build and experiment with pinch devices, stellators, or even other types of machine. But the vast majority of work in magnetic confinement fusion over the last 50 years has used tokamaks. Right now, in the ITER project, the future of nuclear fusion may very well depend on the biggest tokamak ever constructed. But next episode, we'll focus on something else that really began to spring up in the 1970s alongside punk music and Monty Python. Because the lasers that the Culm 5 used to confirm the temperatures achieved by the tokamak would soon provide an alternative to using magnetic fields altogether. The show will now branch off into two branches. We'll continue to explore magnetic confinement fusion, but in parallel, we'll look at inertial confinement fusion, which means frickin' lasers. Thanks for listening to this episode of Physical Attraction. As ever, you can visit us on the web at www.physicspodcast.com, where you'll find a contact form that I generally respond to, unless you are trying to tell me about some new laws of physics you've discovered that no one else knows about already, or indeed how many UFOs you've seen over the last few weeks. You can talk to us on Twitter at PhysicsPod. You can get in touch with us on Facebook at Physical Attraction. On the website, you'll find download links for every past episode that we've ever done. It's more than 100 now. And you'll also find the possibility to donate to the show or purchase past bonus episodes. We have a Patreon account where you'll be charged per bonus episode that we release. I'm sure there'll be one coming soon, but I don't necessarily know what the topic will be on. Until next time then, take care of each other.
Tokamak.